Homework 16, Exponential and Logarithmic Equations, Video 6, Logarithmic Equations, logs equal to a number, Part 2. In the previous video, our example had one log on the left and a number on the right. But this type of equation says logs equal to a number, giving the not so subtle impression that there might be more than one log on the left side, such as in this equation. Solve log base 2 of x plus 5 plus log base 2 of x plus 7 is equal to 3. We really can't do step 2 because this is not in logarithmic form, so to speak. Logarithmic form is log equals a number, and this isn't. This is 2 logs added equal a number. Can we fix that? Can we take the 2 logs on the left and make it look like 1 log? Of course we can. We can condense. Your first move is, if necessary, condense the equation into log equals number. So we need 1 log on the left. Okay, then we can do the rest of the steps. So we need to start by condensing this. And in this case, we're going to use the product rule. Now, all the rules that we saw in the previous series of videos still apply. If it was a minus, we would use the quotient rule. If there were a number in front, we would move it in as a power. But this is the product rule. And the product rule in reverse says if you have the sum of 2 logs, you can make 1 log whose argument is the product of the 2 logs' arguments. So x plus 5 times x plus 7. So it's a little chunky, but that's what happens when you condense. You get 1 log with a chunkier argument. But at this point, we've got 1 log equal to a number, which means we can do the next step, which is to rewrite the equation in exponential form. So if we rewrite it, remember the way to rewrite it is to remember that the answer to a log is the power that turns the base into the argument. So the answer to the log, 3, is the power that turns the base, 2, into this argument, x plus 5 times x plus 7. Now we're not out of the woods yet. We have to finish solving, but this is going to be a quadratic equation, not because of the left side, 2 to the 3rd power is just 8. The right side is factored, but if you're factored and not equal to 0, then this factorization is completely useless and needs to be destroyed. In other words, we need to FOIL this. Factored is only good if you're equal to 0. So if we FOIL it, we'll get x squared plus 12x plus 35. You can FOIL it out if you don't believe me. And now we can subtract 8 from both sides to get this equal to 0. 0 is equal to x squared plus 12x, looks like plus 27. And you're welcome to get out the quadratic formula or try to factor it. I am 99% sure in this homework assignment, anywhere you run into a quadratic equation, if you can't just isolate the x because there's only one term, it'll factor. This one will into x plus 3 and x plus 9. Those are the 2 numbers that add to give 12, but multiply to give 27. So we can set each factor equal to 0, and then solve. So we get 2 possible solutions, x equals -3 and x equals -9. But remember, we're not done. We have to check for extraneous solutions. In other words, we have to check for solutions that might make some arguments equal to 0. In the next video, I'll be writing a new series of steps so I can get rid of these. But we do need to check. And that doesn't mean you have to plug in the number and push it all the way through to make sure it makes both sides equal. That's not a bad idea. But what we're really checking for here is, does our solution cause any argument to become negative? So let's just write the logs, log base 2 of x plus 5. We'll go ahead and write the plus in between, log base 2 of x plus 7. If we substitute the -3, we get log base 2 of -3 plus 5 plus log base 2 of -3 plus 7 And if we evaluate the arguments, we get log base 2 of 4. I know what that equals. Plus log base 2 of, I'm sorry, this isn't 4. What am I thinking? Negative 3 plus 5 is 2. Over here it's 4. Could we evaluate those? Yeah, we could even finish checking to see that it's equal to 3. This is equal to 1. Think about it. This is equal to 2. Think about it. 1 plus 2 is 3. But what we were really checking for is, do the arguments become negative? In this case, they did not, which means the x equals negative 3 is good. But what happens when we check the x equals negative 9? And you can check this visually and verbally and mentally. If I put a negative 9 here, that's a problem. It's not because the 9's negative. It's because after I add 5 to it, it's still negative. So I'm going to go ahead and start the written version of checking this. Here's the expression that involved the logs. And by the way, you need to go back and check in the original expression, not the condensed. And I'll tell you why in a second. But if you substitute negative 9 for both x's, then this one becomes log base 2 of negative 4, and right there we shut it down. It's bad here too. This becomes log base 2 of negative 2. But it only takes one negative argument to shut it down, no. So if this were a homework question, the only answer would be x equals negative 3, because it does not cause any arguments to become negative. Now you might be wondering, so where did the negative 9 come from, and why did it get to be an answer? Well, here's why, and this is why you should not check in the condensed version. This was not the original equation, this one was. But if I plug the negative 9 here, I'll still get negative 4, and I'll still get negative 2. But when I multiply them, it becomes positive. So negative 9 is actually a solution to this equation, but it's not a solution to this one. So when you condense, you're changing what might be the solutions, and you just got to check them in the original equation. A little messy, but it's not really that bad. It's just a tad inconvenient. Just remember, you can't take logs of negative numbers. Anything that causes you to needs to be thrown out.